I think there should be still a lot of students joining, so I will begin maybe in 3 minutes. Okay. Okay, let's begin. Right, so I think there should still be about more than 10 students joining, but we should not wait. Okay, and today we will have another student joining. So basically, he prepared some one of our mini project. Okay, so he will give a presentation of what the mini project is about. It's around I think it's 6 p.m. Okay, and so that's the next mini project. We will do some annotation, and the annotated file will be used for the final project. Okay, because there was some concern about because our department has multiple data science courses, right? Deep learning, data science foundations, and machine learning, etc. Okay, and maybe also data mining, right? So we don't want a student to reuse the same final project across different courses. So we will, at least for my course, we will together with the student prepare some data set, and then for the final project, using the collectively prepared data set for machine learning, okay, for data science project. Okay, so yeah, let's continue. Right, so last time we talked about SVD, right, singular value decomposition, and we spent probably most of the time recap what is eigenvalue, eigenvector, and what is column space, row space, right? So then we actually stop where we give you three key information. Okay, the first information is that we wanna, because let's say each row in the A matrix, okay, the data matrix, n rows and d columns, okay, each row has a fixed length, right? You know what is A1, A2, A3, AD, okay, d dimension. Then this length is fixed. So if we want to maximize, let's say we want to find an axis in the new space that maximize a component that of your row, on this space, right? It's equivalent to if you want to minimize this distance, right? But it's square relationship, okay? So this beta square plus alpha I square equal to your constant length, right? So it's equivalent to say if we wanted this thing squared, right? Orthogonal component. When we talk about component, we square them, okay, because of this reason. If we wanted the component for this xi vector outside this v axis that we will choose to be minimized, right? We want to capture most of the information within the v component, okay? So that means the beta square should be maximized, okay? So put simply, one metric is that we want to maximize beta square, okay? Equivalent to say we want to minimize alpha square, because alpha square plus beta square is equal to a constant, okay? So this is the first thing we want you guys to memorize. The second thing we want you guys to memorize is the form of SVD, right? So SVD really for this kind of A matrix with n rows and d columns. And then when you call SVD, it will give you 3 matrices, okay? The first is a U matrix, the second is a D matrix, the third is V matrix, okay? And here V matrices are written in a transpose form, right? And just to recap, each row is a new, because you are kind of doing dimensionality rotation or reduction, right? So each row here is a new axis, okay? So we have, basically we reduce to R axis, okay? So you have X, Y, Z, 3D space, right? Now it's R dimension space, okay? So how important each dimension is by the diagonal values. D means diagonal matrix, okay? And their coordinate, let's say for this row, right? If we map to this R dimensional space, specify the V, what are the coordinates? It's specified by these R values, okay? So that's the intuition for SVD. And for any A matrix, you can do this. And D are, because these are importance, they are always going to be non-negative, right? Listed from largest to smallest. So the reason we have largest is because this is the largest singular value, where you will find the largest singular vector, the axis that we map the most information with, right? And then we find in the orthogonal space to this V1, we want to find V2, okay? V2. And how important it is, how much component of A is captured by the second dimension is by this value, sigma 2, okay, etc. And we will not tell you what is U for now, okay? We will construct this U later, okay? So this is a comparison, and keep in mind, so we have this relation, ABI equal to DUI, okay? And A transpose UI equal to DBI, right? So just think about the matrix A, right? And V, remember this V is our axis we want to rotate and find a new axis for R dimensional space, okay? So if you time A with any dimensional space, it's equal to DII times UI, right? So UI is, let's go back. Look at the relationship, right? This row is running to this R here, and we run to this column. Okay? This is UI. Okay, so their relationship is specified by this formula. Okay? This formula, and there's actually a comparison with Eigen decomposition. Right? So for Eigen decomposition, you have A VI equal to lambda. Okay, but here we are doing SVD, so this becomes lambda U. Okay, so relevant component. So that's basically the recap of what we see last time. And there's a lot of linear algebra review text that you can familiarize yourself with. But for this lecture, all you need is what we taught so far. Okay, right, so the Eigen decomposition, subspace, vector space, etc. And then what is the shape of the SVD? Okay. Next, we will use the conclusion that we already know to derive really any matrix can be decomposed into this shape. Okay, any matrix A can be decomposed into this shape. This we will strictly prove. Okay. So last time we talked about actually how do you find those axes, the first dimension, the second dimension, the third dimension, etc. Right? We find them by so-called best fitting line. Okay. So think about the best fitting line in the one-dimensional space, right? We want to find the V1, okay, the first dimension, okay? And assume the data only has actually r-dimensional information, right? Even though you can encode it d-dimension, but the other are kind of, actually it's kind of, it can be embedded in two-dimensional space, right? So for example, we can say, hey, we are in a three-dimensional space, but all you care about is in this on this screen. Right? So actually, you are embedded in two-dimensional space for this 3D space. Although we are in 3D space, but actually your data point on the screen can all fit in the two-dimensional space. Right? So even though we are in d-dimensional space, but this A may only just contain r-dimensional information. Okay, so that's the concept. And so then we want to find a V, which is the best fitting one, right? So think about it. We don't really want to find, for example, if you have all the points inside on the screen, okay? It makes no sense to find a axis, right, which come out of the screen, right? You just want to find a line that's on the screen, which probably captures the most coordinates, okay? If you find some axis, some V that face you, right, point out of the screen to you, that makes no sense. It doesn't capture any information in it, right? So how can we find a V that it's a best fit line? Okay, right. So let's think of in this way, right? So remember, so here's our notation. Okay, we have a matrix A, which has d-dimensional, right, n rows. Okay, so usually when we talk about a vector, it's a column vector. But here, when we talk about AI, okay, AI, it's a row dimension. Okay, A1 is first row, and the nth row. Okay. So I don't know. So when I'm in like high school, usually if you are writing a dimension vector, right, you use something like this. Okay, and right. But in college, usually we use a bold face. Okay, right, and we don't have the arrow up there. Okay, so if you are using latex, it's like a mass BF bold face, right? And then you have something like this. Okay, but if you are in the word, just put the big B, right? Uppercase B button. Okay, it's a vector. Okay, if you don't make it a bold face, and it's regular scalar. Okay, let me find my mouse. Oh, I think I used the wrong stuff. Okay, yeah, let's continue. So you think about it. AI is the ith row of the A, right? So then you have a vector, okay? So let's assume this particular A is this vector, right? But now we want to find a particular direction, project this AI into this V, okay? And V has to be a unit vector, okay? Right, it's an axis. We don't have the length, the length is 1, okay? And how do you map this here, right? So you know that the sigma angle, and then you do the cosine theta, right? So this is equivalent to do a, dot product, right? So this is notation for dot product, okay? It's equivalent to, you can also write it like AI transpose. Okay? So this is equal to, for example, you can write an AI and the length of V vector and cosine theta, right? Okay. This is the cosine theta, right? But we know that V is a unit vector, right? Unit vector. So this is GAM. Okay? It's really AI times cosine theta, how much component on this one. Okay? I hope this is intuitive. So next, let's look at the sum of squared projection lengths. Okay, so keep in mind this thing we will see again and again, again and again. Okay, in this lecture. So you'd better be familiar with this. Okay, let's find a right perspective to interpret this thing. Okay, so remember we told you that A is something, A is A1, right, row vector, the AM. Okay. Now, here you see AV, right? So A times V, okay? Right? This is equivalent to this times V, right? So let's use a block matrix notation, right? So you know this is one row, right? 1 times D, okay? So this is 1 times D, okay? And this is what? This is a column, right? So this is D times 1, okay? So what's the result? This is 1 by 1, right? So actually, you can do the block matrix computation. Then you will find it's actually equal to something like this. Okay. This times v, which is the 1 value. Okay. This times v. Finally, it becomes this column vector. Okay. So this is the matrix times the column vector. Okay. I hope this is comfortable. Right. And again, this inner product is equivalent to this. It's just a notation difference. Okay. Right. But the reason we need a absolute value here, right? So we can see two bars. Okay. The reason we want this is because inner product can be negative, right? So we want to be positive. For example, if your v is this direction, your vector is that direction, right? Then your component is negative. Okay. So now let's take a look at what is this, right? So let me okay. What exactly is this thing? Okay. Let me erase some irrelevant stuff. So this thing is actually, you think about it. This is what? This is the length of the vector, right? L2 norm. A square is saying I don't take square root. Okay. This is like if you have a vector which is x1, xn, xd, right? Then your length squared is x1 squared plus x2 squared plus d squared. Okay. That's the result. Okay. And this is L2 norm squared. Now we know that if we know that AV, this thing, right, is a vector like this. This AV, right, is this vector. Okay. Now it's equal to every element squared, right? So this is this thing squared, okay, plus the second thing squared, plus the third thing squared, all the way to here squared. Okay, right. So when you square something, you can think about the absolute value square, also, right? So it's always positive. Okay? So this is physically really the sum of a squared projection length, right? Because you think about it, in this summation, this is actually a summation. Right? Each thing comes summed together. In this summation, this is what? This is a projection for A1, okay? Right? And this is what? It is a projection for AN, okay? So we are really having each row, we have a projection along the direction V, okay? And then this projection value squared, and then sum them up, right? It is this thing, okay? So sum of squared projection lengths of all the rows, right? Gives you this shape, okay? This is very important, by the way, okay? So you need to, put simply, you need to remember this, okay? This AV L2 norm squared is the sum of the projected component of every row, right? Every row in the A matrix. Okay, A matrix is the data matrix. Okay, let's continue. So next, remember we have SVD, right? So we have U, D, V transpose, right? This V transpose, we say that you can write it like V1 transpose, right? Because V1 is a column, okay? This is the direction we want. V2 transpose, etc. Okay? And VR transpose. VR. Right? This is the V transpose. Okay? And how do we find those axes? Right? The first layer, we want to find the V1, the first dimension, that contains the most components, the best containing components, right? For all the rows in there. Okay? Each row is a data item. So remember this thing, right? So this thing is actually exactly what we just described, right? So here, this thing squared is a sum of squared projections, right? If we maximize this component sum, right, which means most information are contained along direction V, okay? We also maximize its square root, right, which is this thing, right? So it's really that we want to find the best fit line, which is a direction V, putting here, it will maximize this value, okay? Which we call this V1, okay? Again, we need to make this V a unit vector, right? So this is what we covered last time. It's just a quick recap, okay? And then we also define, hey, what if we find such a V1, right? And we put a V1 here, and then this value becomes sigma 1, okay? I think we've described this. And the second one is similarly found, but we require to be perpendicular to V1. Okay, and for the case dimension, right, we find case V. Okay, we want it to be perpendicular to all the previous dimensions, right? Because makes no point to be not perpendicular. Those components will already be covered by the previous dimensions. Okay, we want to find a dimension that totally orthogonal. All right. So last time we stopped here, right? So we want to prove this theorem, right? This is if we find by this greedy method, okay, repeat R times until there's really no component outside another V, right? It's exhausted. In this case, we are finding the best fitting space, right? This is the best fit line, and we find the best fitting space, right? So we know how to find a V1. V1 is trivial, right? V1 is already best fitting space, right? So why we want to prove this, right? So this is trivial because these are the sum squared components, right? And take square root, and we find the V1, which is the V that maximizes. This is already the best, okay? But for V2, we need to prove that's the best because we have the component here that's perpendicular to V1, right? What if we find something that has some smaller angle or larger angle than 90 degrees to V1? What will happen, right? And similarly, these requirements are additional requirement, okay? So with this requirement, how do we know it's still the best for the subspace? Let's say V1, V2, V1, V2, V3, all the way to V1, V2, V3, VK, or even VR, right? So in order to prove that for any K, this holds, right? We will use induction, okay? Mathematical induction. So we first show that V1, V2 is also the best, right? So this is the first step. The second step show that if assume we have V1, V2, V3, all the way to VK minus 1 is already the best, okay? We want to show that VK, adding VK is still the best. If that happens, then we can put K equals 3, 4, 5, and the reasoning continues, right? So it's like a V1, V2 valid. Then if V1, V2 valid, then V3 is also valid, right? Now that V3 is valid, V1 to V3 is valid, then V4 is valid. And you just need to prove this induction step, okay? Then we can, here we will show that V1, V2 all the way to VK is the best fit subspace, right? So here we are at this step, right? First, we have the base case. Again, K equal to 1 is trivial, right? V1 is always the best. Want to show that V1, V2 is the best, even though we require V2 to be perpendicular to V1, right? Let's assume that we have 3 space, right? So this is V1, V2, right? Then you know that the span generated by the 2-dimensional subspace is this space, right? And then now we want to prove by contradiction, which means we want to claim that, hey, this space is not the best, right? We can find another space, let's say this space, okay? And along with V1, V3, right? And this space is the best, not this space is the best, right? This space is the best, okay? Capturing your A, right? Different points in the 3D space better, okay? We want to show this subspace is best, right? And then we basically, because this is proof by contradiction, we will show, hey, this is impossible, right? Then you have to be worse than this space. Okay? So this is what we are trying to do in the base case, right? So now we are saying, hey, now assume that you can find even better. Like the W is the actual best fitting 2-dimensional subspace, not the one that we generate with V1, V2. Okay, right? We want to show this impossible. Span V1, V2 is going to be a better one. Okay. How to show this? Right, and we know that this is a 2-dimensional space, right? So we can always find a orthonormal basis W1, W2 in the space. Okay, and sum over the squared projection will be something like this, right? Okay, and what does it mean by the best? Right, so but best means, you know, this is a component along W1, this is a component along W2, right? If you look at our, remember I asked you guys to remember this shape, right? So this is if you remember AV and it's square, right? Okay, so this is a component along W1, component along 2, right? The summation, we hope it is the largest, right? It captures most of the components, okay? But then we will prove this. We will prove, hey, this is impossible, right? The component is gonna be smaller than that consists of V1, V2. Okay, at least not better. Okay, right. So then V1, V2 is really the best. Okay, this is a contradiction. So we do not find a better space. Right? For if we can find such a better space, then any W1, W2, we can always find a valid W1, W2, such that we have this. Right? So we have more components than V1, V2. Okay? Now we want to show for any space, it's like the other direction. So there's no such two dimensions, right? That will satisfy this. Okay, so W is not a better superspace of two dimensions. Okay. Yeah, let's go through the proof. So now that we have a particular W1, W2 that we want to beat V1, V2, right? Let's first pick the trick to prove this is pick from the end. Okay, let's pick the second W2, right? First. So how can we pick W2 from the two-dimensional subspace W, right? We can pick W2 to be orthogonal to V1, right? Because we already know V1, V2. Okay, how we choose that? That's using the greedy method. So this is always possible. We can prove it, right? So for one case is if your W, this subspace, is already orthogonal to V1, right? If that is the case, then any vector inside this W, like W2 is also orthogonal, then we are done. Right? But the second case is, for example, we say, hey, this may not be the case, right? Your W may just have a small angle, right? So the V1 has some component, how do you say that? Yeah, V1 has components along the W subspace, right? So if that is the case, we can write it out like this, okay? Something like this. It's like this is your, let's say W space is two-dimensional, okay? This is a W space, and this is your V1, okay? V1, V2 is already pre-computed. And there's an angle here, which means you have some space along this face, which is this projection. Okay? And then you also have some perpendicular point. Okay? And so, by vector summation, this thing plus this thing equal to. Okay? So we can always, if it's not orthogonal, we can always find some projection on it. Right? Otherwise, there's no projection, then case one. If that's the case, then we can simply choose W2 to be perpendicular to W1. Okay, it's a parallel component W. So this is going back to our previous example. Right? Although your V1 is not perpendicular, but you have a component right on this W space. Okay? Then all we need to find is to find another vector that is perpendicular right, to this component. If that's the case, we can show that this thing and these two are also perpendicular. Okay, so if you move things here, you'll find that this is also perpendicular. Okay, so this is a visualization of the conclusion, but you can, again, so you can prove it mathematically. Right? So why, if we choose W2, right, our goal is want to choose W2 to be orthogonal, which is achievable. Right? Case one is like this. If case one doesn't hold, then you must have a projection on the W, right? And then we can choose a W2 inside this W space to be orthogonal to this projection. Okay. So how can we prove that? Right. So if we choose W2 to be perpendicular to the projection of U1, then we can show that W2 is also perpendicular. Right? So this is by this proof. Right? We just want to show this. We just want to show that the inner product of these two vectors, right, equal to 0. Then they are orthogonal. Okay, this is following the definition. And so we know that V1 is what? V1 is this. Right? So we just write it out. And the inner product can write it out right, in the sum. Okay. And we know, so this is 0, right? Because, for example, this component is 0 because of this thing, right? They are orthogonal. They are inner product. This is 0. It's even simpler, right? Because this is a perpendicular component to your W space. Okay. And this W2 is a vector in the W space. Okay. Of course, they are orthogonal. Right? So these are 0 plus 0, which is 0. Okay. So this, if you really want to prove it, you can do something. Okay. now that we know that W2 can be chosen from the subspace that you think is the best for your two-dimensional, right? If we choose such a W2 there, right, then we can show, following our definition of V2. V2 says we want a V2 to be orthogonal to V1, and V is that orthogonal to V1 unit vector and maximize this. Okay, right. And the W2, what is W2? Let's take a look. W2 is orthogonal to V1, right? So this condition holds. Okay, and W2 is also normal. Normal means a unit vector. Okay, so it's really the case, right? So it's really, W2 satisfies this requirement, and we know that V2 put here maximize this value. Okay, maximize this value. Of course, your W2 cannot go beyond that, right? So this is a upper bound now. Okay, and similarly, we have this, right? So it's not similar. This is just following the definition, right? Because if you look at V1, right? V1 is finding a particular V1 maximizes already. Okay, so of course it's trivially larger than any other that is unit vector. Okay, so now let's combine these two conclusions. Right? So we sum this equation with this equation. Right? Sum of the left-hand side, sum of the right-hand side. We get this. Right? What does this tell you? Right? The component in this W space, okay, is going to be no larger than the component along the V1, V2 span space. Okay, so this shows that K equal to 2, V1, V2 is the two-dimensional space spanned by V1, V2 is really the best. Okay, so that's the property. Okay. So you can see, hey, it's really the best, right? Now we want to generalize this to K, right? Assume that all the way to K minus 1, the span is the best fit. K minus 1 dimensional space. Okay. Now let's consider K dimensional space W. Just like before, we can pick a WK that is orthogonal to the previous K minus 1 subspace. Okay. And the method is similar, right? So if you're orthogonal, then to the previous space, and that. If it's not orthogonal, you get a projection, and you find a vector that's perpendicular to that projection. Okay, and you can show. So this is by induction, right? This is we assume this is the best fit, which means all the K minus 1 component summation is going to be no more than V1. It's the space spanned by V1, V2, all the way to Vk minus 1. Okay, so this is the induction assumption. And now we also know that choosing this, we have this, right? So this is because, Vk is a vector, it's a unit vector that maximizes while being perpendicular to this, right? Wk is just a yet one vector that is perpendicular to space and a unit vector, right? Of course, Vk is the one that maximizes, right? This is going to be larger than this, right? Now the conclusion is pretty simple, right? So you add up these two inequalities, okay? Add this to this, right? Combine with this, okay? So this minus 1 becomes all the way to K. Okay? That completes our proof, right? So again, this K can carry over to any number, which means the previous method, those V's that we find is really the best fitting V's. Okay. Any questions? So this completes the proof that we left over last time. Okay. Keep in mind, we are not talking about anything else than V. This V is pretty intuitive, right? You just so right now, all you need to do is right? You just rotate any unit vector on all the directions, and it will give you this magnitude, right? And you find the V that maximizes. We are not yet talking about how to compute this V, but this V must exist, right? You just manually try all the directions, okay? And the second dimension really, hey, you try all those, but don't be perpendicular to V, right? And these are defined V's, and we show that these V's in this way is the best, okay? So this is what we just proved. Okay, so far we just talked about the right singular vectors, right? V1, V2, V3. Okay, they're called the right singular vectors. Okay, and then what we will do next is we define sigma, singular values, and using right singular vectors and our defined singular values to define left singular vectors. And finally, based on this definition, we derive that, hey, our A can really be, decomposed into SVD shape, right? And each column, each row are really of these singular vectors, okay? Right, so this was what we will be doing. It's like we are having the conclusion and we will verify whether this conclusion is true or not, okay? It's like how we find it is like a magic, right? But now that we assume that you already know it, right, we can verify these things are really like that, okay? So now we define, right? So remember, if we have this thing squared, it's the squared component, right? Along the first dimension, square the components of all rows of A, and then along this direction order, right? So now we remove this square, okay? And if we without this square, then we call this a singular value. Right? So basically for V1, if you put V1 here, this is your singular value for the largest singular value. Okay? If you put V2 here, this is the second largest, okay? Right. So again, there's a stricter relationship. Sigma 1 is going to be larger or equal to sigma 2, larger than or equal to sigma 3, etc. Okay. This is also very easy to see, right? Because, if you look at our definition here, right, we really want to maximize this, right? Maximize sigma 1. Okay. Of course, sigma 1 is the largest. If sigma 2 is the largest, we will choose V2 instead of V1 here. Okay. And this carries over to here, right? And V3 is larger than after V1, right? You will choose V3 instead of V2. Okay. So it's really the sigma 1, sigma 2, sigma 3 are becoming smaller, smaller, and smaller, okay? Or almost equal to the previous one, right? So this is the singular values, and these are actually the elements on the diagonal of D, okay? SVD's second matrix. Okay? And finally, we want to show that if you remember SVD, right? So here we are doing this is V1, V2, V3, and we have the diagonal values, and we show these are these values. And then remember, we have a U matrix, and we have those columns, right? And we are defining what's it. And finally, now based on these defined elements, we want to say, hey, we can put them back in this shape, and this is really it. Okay. This is what we are trying to do next, right? So what is U? So we are defining this, right? So we are basically going from conclusion back, okay? Because if you remember, we have A times VI equal to what? Equal to sigma I UI, right? This is what we discussed about, right? And here we are defining UI by move this down. Okay, so this is what we are trying to do. Okay, because now that your V is defined, right? So the argmax, okay, and now A is so one we already know, right? So then with A and V, then you define sigma. Okay, right. And now that we already define V, we also define sigma. Right? A is the input matrix. Then we also define V. Okay, so this is pretty natural. Now, given those components, given its conclusions, we derive that we can really putting them back to this kind of shape. Okay? Again, keep in mind. Sorry, let me see. This is page 27. Keep in mind, right? So this shape is really in matrix form. It's like this. Last time we derived this, so I will skip a little bit. We just prove this. It's equivalent to prove the matrix shape like this. Okay, so we just prove this one. So in order to prove this one, it's not so straightforward. Okay, we need to have a lemma to help us prove this theorem. Okay, and the lemma is something that you prepare for a more complicated theorem. You do some preparation for this. Okay, I see some papers people just say, "Hey, I prove lemma 1 all the way to lemma 10." So there's no theorem. So I think they are misusing it. Okay. So first, let's see how we prove this lemma, and let's understand what is lemma first. Okay, this lemma is saying this, right? If your two matrices are exactly the same, which means every element is the same, okay, in the matrix, then this if and only if, right? So if and only if, then if A and V are the same, then for any vector AV equal to BB. This is pretty simple, right? Because A is B basically, B equal to A, then AV is AV, right? It's straightforward. What's tricky, right? Why this thing is worth discussing is this direction, okay? Because if and only if. Okay? This direction not so simple, right? So if you have some A and B times the same vector, it's the same. Is there any guarantee that A and B are the same? Right? Typically not. But here we are saying for any V, right, you put here, they will be equal. Then this actually makes this become true. Okay. But let's see how we can prove this, right? Especially the reverse direction. Okay. So we are using this conclusion, this thing. Okay. EI is a column vector. Okay. EI is a column vector. The other part is 0. Okay. The ith location is 1. The other. Okay. Now let's look at a matrix A. Right. This is A. This is EI. Okay. Let's see what will be the result. Right. We know that A times a column vector is a column. Right. It's equal to column. But let's look at what's the result. So first, let's look at the first row. Okay. The first row, and again, so you see the ith column. So let's put I here. Okay. This is the ith column. Okay. Let me so this is the ith column. Okay. Okay. Next, let's look at how do the inner product. What's this value? This value is really this thing times this column. Right. Give you this one. Okay, but the other location is 0, right? Only this is 1, which means the ith, this ith, okay, 1, okay. Which means this value is this value. Okay, this is exactly this value, right? And let's look at the second row. Second row times this column gives the second row, right? And again, the other values are 0, right? Only this value times this 1. So this value is this value, okay? Right. And you can show that after time this, this is really this ith column, this column. Okay, this is conclusion. Right. So basically, this is also what we do, saying telling you that times the diagonal matrix. Right. On the right, it's scaling the columns. On the left, it's scaling the rows. Right. So similar, if you have the row vector here. Right. So let me see. If you time the row in EI, which is row vector on the left, you get the first row. Okay, there's an ith row. On the column vector on the right, you get the ith column. So that's the conclusion. Let me get control of my mouse. Now, if you have this conclusion, then that's pretty interesting here. Okay, then you can prove that the other direction. Right. So, how to see this goes there? The answer is very simple. Right. So you told me that it can be any V. Right. It can be E1. Right. It can be E2. Right. It can be EN. ED. We have D dimension. Okay. So what does this mean? This means, right, the first column of A is the same as the first column. Okay? This, if you put E2, the second column A is equal to the second column, right? And all the way to D dimension. This means every column A is equal to every column B. Then I think it's pretty obvious A equal to B2. Okay? Right. So that's how you can prove that. But every column is the same, then your matrix is the same. Okay? And again, this is saying, hey, this is any V, so I can just put an E1, E2, E3, these special V's. And we can show that every column is the same. Okay, so this completes this direction. So now we say that if we can show that given two different shaped matrix of different forms, but if we put the V on the right-hand side, and we can show that for any V, okay, for any V, right, and they are the same. Then A and B, these two matrices also. Okay, so this is the lemma we have here. Now we are ready. Okay. So the reason is very simple. Now A is still the same, right? And we want to prove B is the same. Okay, this is B. Right. And all we need to do is we just time B on the right-hand side. Right. Okay. And then we show that they are the same for any. Right. So here, let's first do this. Right. So we time a VJ here. Okay. We time a VJ because this can be for any. Right. So let's see what will we get. Okay. And so let me see. Let's see a few steps. Yeah, let's time VJ. Okay, if we time this thing with VJ, right, on the right hand side with VJ, what do we get? So we can see that So here, this is how you see it, right? So this is a summation of terms. Right? This is like one term plus one term plus one term, and times Vj. Okay, but let's look at which term really matters here. Okay, the other term doesn't matter. Okay, the reason is very simple. Right? So Vi, Vj, they are orthogonal, right? Orthonormal, right? Which means if they are not the same, I and j are different, then this thing is zero. Okay, they are orthogonal. They are 90 degrees. Okay? So there's only one term in this summation that is not going to be zero, which means it's I equal to j. Okay, this is j. Right? So this gives you something like the summation is gone, but this should be j. Right? This should be j. This should be j. Now, if we have this, then the other conclusion comes in, right? So it's Vj transpose times Vj, right? It's an inner product of a unit vector. It's 1. Okay? So if this term becomes 1, right, and then you only have this term now, which is sigma j uj. Okay? So this derivation is actually a little bit complicated for now, but later you should see this immediately. Okay? We will not say in so much detail. Right? So this is our conclusion. Okay? If you times the right-hand side with Vj, you get sigma j uj. Okay? And sigma uj is actually equal to a Vj. Right? And you may be curious why. Right? So this is because our uj is defined this way. Right? And sigma I ui equal to a vi. Okay? This is by definition. Right? And because of the definition, right? So ui is basically defined as avi, and vj, uj is defined by avj divided by sigma. Of course, times sigma j is avj. So now we have this conclusion that we will carry over to the next page. Okay? We'll do this a lot of times in this slide because there's no more space to run. Okay? But keep in mind this conclusion, right? And we will continue on the next slide. Right, this is the next conclusion we just derived. Now, this is kind of close, right? You see this A and this straight, they are timing a particular Vj. Okay, they are timing a particular Vj, and we show they are equal. This is not enough. We want to show for any V, not just a Vj, this whole. And then based on the lemma, this thing is equal to A, okay, which can prove this. So how can we use the previous conclusion we derived here to scale this to any V? So any V is of this shape, right? So we can write it like this. Remember, we say that the A actually only contains R-dimensional information. That can be derived by V1, V2, by V2, V1, all the way to VR. Okay, right? And then we can write. So if your vector V is in this subspace, you can write like this, right? You have some component along V1, some component V2, something. But now we want to say it's any V. So that's gonna be another component that get out of this subspace. Okay. So this is our shape like this. So now this V is a arbitrary V, right? You can always tune the CJ right, in different ways, and then leave the rest of the component on the last one. Okay. So, and here we require this component to be outside, right? Otherwise, some component can be put in. I just see CJ, okay, to make sure this happens. Okay? So now let's look at this, right? So we want to show that AV, right? Any V equal to this thing. Right? So let's see how to prove it. Okay. Now AV, right? But V is this thing. Okay. You put this thing here, you will get this thing. Right. So how do you see this? It's by this, right? So A times V is this one. First times this, right? This gives you this. Okay, because this scalar, you can move to C before. Okay. Then A is also times this, right? And this is 0. Okay, so how to see that? This is actually very simple. You think about it, what's A? A is the first row, A1, this is AN, but N slow. Okay? But then you times, remember this is a component VR plus 1. Why this is 0? This is because we show that A is within this space. Okay? right? So the A1 is within this space, okay? But this thing is totally orthogonal to this space, right? And their product, this times this will be 0, okay? Similarly, the second row and this is 0, okay? The last is 0, okay? So this is 0 vector. Okay? You can see it's in board face, right? It's not a simple 0. It's a board face, right? It's a 0 vector. Okay? All right, so if this is okay, then we can ignore this component now. And let's look at here, okay? So what I mean is we just need to look at this component, how it will put this on, right? And next, it's our turn to put, A back in. So, so just look at this AVJ, okay? AVJ, right? This is from the last page. We derive this equal to that. Right? So this basically is saying, hey, now your summation over JCJ is still here, but your AVJ is now replaced with this. Okay, so this is what we are doing here in this step. Hope everyone can follow. All right, so now let's see which component can be moved forward. Right, so you see this component is J, J, and we also have J here. Right? And the other components are I. Okay? I. Right? And you can take out, for example, you can move this J outside. Right? And then you have a component with I and another component J. Okay? So this is a component J, basically. And you can swap them. Okay? Because now it's kind of quite clean. So you can swap, right? It's like a 2 parentheses size summation term. Now, actually, now we have another trick, right? So we can put this component back, okay? Right? So why they are equal, right? So if this obviously equal to this, right? But we have additional component, right? But that's also very simple, right? You think about this term times any term in the previous term, it's 0, right? Because you think about it, these are, within the R dimensions, right? Okay, and this R plus 1 is orthogonal, okay? So they are also orthogonal, right? They are in the product. These two is going to be 0. Okay, so adding this term doesn't add anything because these two terms are taking the product 0. And so again, then we basically prove the conclusion, right? So A, V equal to this thing, right? Again, this thing is V, okay? This is after adding this back, yeah, this is just, right? And keep in mind that now we prove this. For any V, AV equal to this thing, right? And A is equal to this stuff, right? Now this shows that if we define, let me see where we define here. We define, after we tell you how to find V1, V2, Vr, right? And we define sigma like this, and then we define the U like this, okay? And we show that you can really put things back into, into this shape, and this is really just A, okay? Yeah, any questions so far? I hope this is fine with you guys, okay? Again, we will have the video shared, so you can watch the video, and I think that you can recap what we just described. Okay, just looking at this slide may not be that helpful because there are too many notations. The lecture is important. Okay, and we just told you last time how this thing is equivalent to this matrix multiplication. Okay, so I will not repeat that. Okay? Just to use a block matrix notation, write them out, you will see. Okay, and again, we have the video for the last lecture. You can take a look. Next, let's look at the concept of SVD with Frobenius norm, right? What's the relationship? So how many, who can tell me what is Frobenius norm? Anyone can tell me? What is the Frobenius norm? Yes, there are a bunch of norms for matrix, right? So the for scalar, it's absolute value, right? -2 if you take epsilon is 2, right? How large your scalar is. For vector, we have L2 norm, right? Vector length. You can also define any LP norm, or you can define some other values, right? Okay. And for matrix, we also have so-called how large the matrix is, right? And we have the one kind of norm is called a Frobenius norm, right? We also have two norms. We will see that later. Okay. So yeah, so let's recap what we defined earlier, right? So if you put vi here and then compute this component, take square root, it's sigma. Okay, this is a singular value. Okay, this is a component of A along vi. Right. Now we can prove this. Okay, summation of all the components of the singular values. Right. So you have the singular values and you square them and take the sum. Okay, right. And then remember, square them is really the component, right? The component without taking square root. Right. And this is along the first dimension, second dimension, all the way to last dimension. This is from 1 to r. Okay, just in case you don't know what it means. And this is really equal to Frobenius norm of A. Okay, what is Frobenius norm? Chrominius Norm is saying that if you have a matrix, okay, you have A11, A12, right, all the way to let's say ANN, okay, NN. So Chrominius Norm is saying that we will take every element square, okay, we'll take this squared with squared, and then sum them up, okay, and then we take a square root. Another way to look at Frobenius norm is you vectorize the matrix. Right? You list the rows, and then the second row list here, and the third row list here. And you vectorize the matrix, and you compare L2 norm. Right? It's basically every element squared, then take the sum, and then take the square root. Okay? If you are familiar with machine learning, these things are also, you can implement using mean square. Right? It's a sum squared. You don't take them, divide the number of elements here. Okay? So this is Frobenius norm. And it really reflects how large your matrix is, right? But basically, every element in the matrix is squared, and then takes the sum. Right? And if you square it, then you don't need to take a square root. Okay. And we want to show that these two are the same thing. Okay. So let's take a look at how we can prove this. Okay. So let me see. Let's see how long we have, because I think Bahadhan will join in 5 minutes. Bahadhan, are you here?
Dr. Yan, yes, I'm here.
Okay, yeah. So are you ready to present the project? Because we need to take some break. So I don't want to, when you present, then we continue. Then there's no break, right? So I will stop here and continue maybe after the break. Okay. Now I will give the control to you. Right. You can describe the project a little bit. Okay. For
sure.
Yeah. Well, we will release maybe tonight. Okay. And the mini project too.
Okay. Sure.
No.
So can I share? Yeah.
Yeah.
So thank you, Dr. Yan. Hello all. So I am Badhan Joy. I have been working with Dr. Yan in a research project. So let me present very briefly like what we are going to do. So can you view my screen?
No, I think you didn't share.
Oh, sorry. I have to share my screen.
Yeah.
Okay.
Yeah, now we can do that.
Yeah, we can see it now.
So our goal is to find the total number of colonies in a cell culture plate by using machine learning and computer vision. So at first, what is like iPSC cell? iPSC cell is one kind of stem cell that can be derived from skin or blood cell and guided into becoming any kind of cell. So from iPSC cell, we can grow our blood cell, we can grow any kind of organ. So because of this, it's at lots of medical use. For example, it can be used in regenerative medicine. So if you have blood cancer, like the doctor can get your skin cell, turn it into iPSC cell, and from there it can grow your blood cell. Same for you have anybody has lung cancer, so it can be used to generate an artificial lung. Because of this thing, it has lots of applications like regenerative medicine, drug testing and discovery, or disease modeling, etc. So because of this, like it is an active research field, and researchers need lots of like iPSC cells to generate in laboratory. And we need an efficient method of generating the iPSC cells. One method is by reprogramming human fibroblasts. Human fibroblast is one kind of skin cell, and we want to better understand how we can reprogram a human fibroblast into stem cell, and what kind of like epigenetic regulators like accelerate or decelerate the process. So how it's done in very brief, it's like researchers take that human fibroblasts in cell culture plate and say they do reprogramming 1. So after 21 days, say some stem cells are generated. They do in lots of parallelly, they change something and say they call it reprogramming 2. And after 21 days, some stem cells, the human fibroblast converts to stem cell. So in another reprogramming, maybe this is generated. And then what they do, after 21 days, they color those iPSC colonies, and they take the cell culture plates under microscope and count them manually. And one iPSC, cell culture plate may have hundreds of like iPSC colonies, so it may take hours to complete, and it's extremely tedious, and needless to say, it's error prone. And human bias can affect counting, of course, and researcher may have a tendency of preferring a reprogramming method, and he can overestimate that method. So we need an effective, unbiased way of calculating those iPSC colonies that would be fast, less error prone, and devoid of human like judgment. So it should be agnostic of human judgment. So whatever I have said, it's just described in here, so that like you can go through it. Here, just this is an example of our plate, cell culture plate. So here you see there are some bubbles that are circled in yellow. There are some reds marked. Those are single cell colony. I will describe what those means. And there are some green. Those are identified as merged colonies. And there are some orange. Those are called single amorphous colony. So just after human counting, you see there are like 110 colonies. There is another example. So some regions are marked, and you see that there are 74 colonies in this picture. So we need to annotate single colony, amorphous colony, and merged colony. And here, if we are not interested in regions which are very small, and we cannot determine or those regions, those are undetermined or undistinguishable, or air bubbles. So at first, how do we define single colony? So single colony is regular shaped, and it would be kind of uniform, round or ellipse shaped, and it would look just like this. So this is a single colony, this is a single, all are single colonies. And sometimes we see a regular shaped colony surrounded by much lighter non-uniform satellite region. We can just ignore those kind of regions, and we will mark only those central region, or like the deepest region that's kind of circular. So for example, here if you see, here, so those are all the satellite regions. So we can just ignore this and we can just mark this region, just like this one. And here you see there is a central region and there's just lots of region. We can just ignore this place and we can just consider only this as a single colony. And then it is amorphous. So from the diagram, it's pretty sure like it doesn't look any, it doesn't have any round or like ellipse shape. So we can just mark it as like annotate it as amorphous colony, just like this. Maybe this is the region we can mark as amorphous. This is also an amorphous region. Okay, so, let me. Then merged colony. So merged colony is there will be a kind of visible merge of two colonies. For example, if you see here, it seems like there were two colonies that has been merged in this region. So we will treat it as merged colony. So, and we will annotate just like this, like the it is blue. The blue border we will see, like we annotate it in this way. So we will annotate it in this way. So this is also an example of like merged colonies. So two colonies may have merged in here. So another example of merged colony. So two colonies has merged in here. And on the last picture here, we can see like it's kind of like it seems like three colonies has merged. So we'll annotate is a merged colony, and then we have to count it as three. And very small colonies. So like which one we should treat as a very small colony? So we are defining our problem. So if we find it too small to annotate conveniently, then we can treat it as a very small colony. But you can go and if it's possible to annotate, just go ahead and just annotate it anyway. But if it's too hard, just we just leave it and do not annotate. And very small colonies, eventually will not count those. And undistinguishable region. So undistinguishable region is like, it would be very low density. So you remember, like after the reprogramming, when we get the like IPSC colonies doesn't have color. We have to color it. So we apply a reagent, and IPSC colonies absorb those color, and it becomes yellow. It becomes blue. And from this picture, you see that like it did not absorb that color properly. So in here, it did not absorb this color. So we can assume it as an like undistinguishable region. For example, this one, there is actually no absorption. So we can assume it there is an undistinguishable region. Here also undistinguishable region. We are not going to annotate those, and we are not going to count those. So there are only three regions we will annotate: single colony, amorphous colony, amorphous colony, and merged colony. So in next one, I will give. So IPSC colony. So these three we have defined. Single colony, amorphous colony, and merged colony. We would define those in VIA, and I have annotated this one as an example. This picture, and I believe Dr. Ian would share it to you all. So just I have annotated all those single colonies in here, one by one. Here I have annotated the amorphous colonies in this picture. And here I have annotated the merged colonies I have found in here. And this is definitely like we will annotate all the colonies in a single picture. So kind of this would be the final output. So this is the end of my presentation. And if you have any questions, yes.
Okay, thank you, Bahan. So basically, what we'll do is we have those colonies, right? So we will have 3 kind of colonies. And there's a software called VIA. We will share a manual how to use the VIA with you guys, okay? And then the assignment will ask you to download that software where you will define those 3 labels, and then you will plot a polygon, okay, around those colonies. And then I think maybe, yeah, I will release it.
Dr. Ian, do you want me to demo that?
Yeah, if you can, please.
Sure.
Yeah, thank you. And by the way, so this is really for final project. This project is for annotating, and then every student annotate one, then we will have probably many, right? So then we will use that to train a image segmentation model, right? And later when you see a new, like this kind of colony image, right? So we hope the model will automatically label them for us, right? Without any additional efforts. Okay? So this is really for training purpose. Okay? So yeah, so the final project will be image segmentation to segment all those colonies, okay, from the background. And here we need some training data, so we are basically this assignment is for getting the training data, right? And familiarize with you guys on VIA, which is a software for annotation, right? Later, if you want to do computer vision project, you know how to do these kind of things, right? From end to end. From annotation, giving labels, right, finally to detection, okay? And the final project will be working on the segmentation model. And there have been a lot of segmentation models there, out there. We will give a list, and you can choose any model you feel interested from the list, okay? We will get the final project details later. Okay, yeah, just go ahead.
Okay, thank you, Dr. Ian. So let me share my screen again. So we have prepared a document. I will go very briefly through this document, and then I will just do one. So we will share this document with you. So we can download VIA from here, and then we have to start VIA. Okay. Let me start. So once you download VIA, so it would be there would be a via.html file, just HTML file. Just open it in browser. Once you open it in browser, it would be opened in something like this. And from here, you can add files, like add your image. So you can add as many images as you want. So maybe just to demo this one, control select. So you can select as many images as you want, open, to be opened in here. So say I want to annotate picture 2. I select this one, and then we have to define some classes. So it would be something like, okay, let me just define one. I have already created a class, so it's pretty simple. So you just add class in here, add a name here, class, name class, select the type as radio, and you just select some IDs. So we have defined those IDs. So we strongly recommend you using the same IDs that we have proposed, because ultimately everybody would share others' annotations. So the annotation we are proposing is single colony, amorphous colony, and merged colony. So those three are defined in here. So single colony, amorphous colony, and merged colony. So we have to create those three, and then the picture you want to annotate, you select this one. Control, like scroll bar, like it will zoom in, or you just zoom in or zoom out, and then we have to annotate this. So we will always use this polygon, not the other one. Always use the polygon, and let's make it a little bit larger, and we start annotating it. Clicking it would select, click. When we are done annotating, we have to like enter, we have to press enter. Select anything outside of this region, select on this region again, and then we have to choose the class. So from this shape, it seems like it's a single colony. So we'll just select single colony, and it's done. And say by mistake we annotate this place. So we can delete it by, at first we have to select enter. That means after we press enter, an ID would be assigned to this region, and then we just go here and click on this. So it will delete the region. So if you want to delete this region, select this region, maybe zoom out and delete this region. So by this way, we have to annotate all of them one by one. So you don't have to annotate all of them in a single go. Maybe you can save the annotation in as an export, or you can save the complete project where it will have all your class, everything, and all those images you have already loaded. Just save the project and save. So it will be saved as a JSON, and you can just load the project anytime. So you just select a project, select an image, and annotate it. So to annotate, always use polygon region, zoom in, so maybe I have, okay, enter, single colony. Maybe let's annotate this one. So okay, I'm doing it. Merged colony. So in this way, like, we have to annotate this, and once annotation is done, we'll just export it as CSV, and we'll just share it with others so that like they can use your annotation. So we have all of those processes described in this document, and we'll share it. Dr. Ian will share it with you today, I think. So this was all from my side. So I'm stopping my share.
Okay, thank you, Bahan. So we will prepare the documents and share you either today or a little bit maybe tomorrow. Okay, and so we will distribute the files, and the real goal is to familiarize the students with annotation tool, right? So so we will not ask you to annotate 10, just maybe 2. Okay, so we will see 1 or 2, at most 3. I think maybe 1 or 2, right? About 2 at most. Okay, and each one may have a lot, right? So do not wait till the last moment. Okay, yeah, thank you, Bahai. Okay, so yeah, let's take a maybe 10-minute break, and then we will continue with the lecture. Okay, thank you.
Thank you, Dr. Ian.
Thank you, Bahai.
Thanks for the talk. That was cool.
Thank you.
Thanks. Okay, so let's I think it's 6:20, so we will come back at 6:30. Okay, and I will continue with the SVD presentation. Okay, and after that we will have a written assignment on SVD. Okay, so of course it will after the annotation assignment. Okay, we don't want any overlap. Okay, right. I will see you guys 6:30. Thank you. Okay, so I think it's a time. Okay, let's begin. Let me see. Yeah, so before Bahada's presentation, we were talking about let me see, the correctness of SVD, right? So, but we didn't tell you a lot of things, right? So like why this is the best, except for the V's are the greedily mapping, and it's the best fitting space, right? And also we of course we can show that you know, one thing we are pretty sure is V's are orthogonal, okay, unit vectors orthogonal because of how we choose these vectors. Okay, let's see, right? Let me see. I think this page, yeah. So we require them to be orthogonal. But for you, for example, we just define something like this, right? So we just define this, and we didn't tell you that you are unit vectors and they are orthogonal, right? And they are unit vectors for sure because this AV, this is it's a vector length of it, right? So it's normalized. But why they are orthogonal, we also didn't tell you, right? And for the next few slides, we are trying to prove these things, okay? And really convince you that SVD, the shape is like this, and it has so many elegant properties. Okay. So this is the correctness proof, right? That we see before the break. And next, let's take a look at the relationship between SVD and the Frobenius norm. Okay. And the relationship like this. Okay. So if you add up all the singular values squared, right, it's equal to the Frobenius norm squared of the matrix A. Right. So to prove this, let's think about, you know, we assume that the spans of those R dimensions, right, of the matrix A, V1 to VR that we defined earlier, right? And so, you know, if we have another vector V that is perpendicular to all of them, right, V1, V2, all the way VR, right? Then we are pretty sure that, you know, for such a vector V, right, and the inner product between the V and any AJ, any row of the matrix A is 0, right? So we told you the reason, right? So because, you know, V, you know, A is in this space, okay? A is some linear combination, like C1, V1 to CR, okay? Summation, okay? And then you time V, then you basically, you know, V and this is orthogonal, it's 0, and V and the VR is orthogonal. So basically you can derive this easily, okay? So if you want to intuitively see this, it really, you know, A is inside this span, right? And the V is perpendicular to this space. Okay, so that's it, right? So this is one conclusion we have, and if you know this, right? So then we know that, you know, we only need, if we consider the size, the vector length squared of this AJ, this jth row of matrix A, we can just compute it as the R components, right? Only these R components, you know, there are some components not 0. Okay, going beyond the other components, you know, this row has no component outside this space, right? So then it will be 0 at 0 for anything else. Okay, so we just have components along these R dimensions. Okay, this is something like this, right? So we have V1, V2, all the way to VR. Okay, and then we have A, which is really only inside this space, right? And then what's the vector length square? This is really, you know, if you look at the coordinates, so this is the first coordinate, it's in the product AJ V1, okay? And the second dimension is AJ V2, AJ VR, okay? So this is the other coordinate, right? So we have x1 to xr, okay? This is the coordinate, and the L2 norm squared is x1 squared plus x2 squared to xr squared. It's really this, okay? Now let's look at the Frobenius norm, right? We want to expand the Frobenius norm so that finally it's equal to the left-hand side, okay? Frobenius norm, as we said, it's all the elements squared, right? So ij is the highest row, jk, okay, jth row, jth column. Right? And if you look at this inner summation here, yeah, so let me see. Okay. Yeah, if you look at the inner summation here, right, and this is telling you, hey, for a particular row J, right, what's it's element-wise summation, element square summation. Okay, it's really this row vector length square. Okay, and if you look at the next step, right, so this is just a because this thing is this thing, that's what we just copy, right? So and so these two summations can swap, right? So I hope you understand this. Right? So these two can swap. This is the property of the summation. Okay? And then here we will swap these two, right? So originally it's I1 to R is inside, right? So now we put it outside. Okay? So we swap them. And next we get this calculation. Okay? So this is because we have shown to you, right? So what is this? Okay, this is really this. So basically, we tell you that let's say given a particular VI, okay, a particular dimension, A have a lot of rows, different things, okay? And there are component along VI square, right? And it takes sum of all the rows. Okay? That's this. So these two are good. I hope you can see this now. Okay. Right. So and if you remember our definition, right, we define this thing to be sigma I. Okay, this is our definition. Right. And so basically we can prove the conclusion. Okay. Any questions? Any questions about this property? So this is let me give you some intuition. Right. So basically the whole information of A is captured by the Frobenius norm, right? Every element square. But this information can be decomposed into different layers. Right? So sigma 1, right, the first singular vector, singular value has one component, right? And sigma 1 square. And then after that, you have sigma 2 square, right? Sigma 3 square. All of them add up to this. Right? So later we will see that later it will be even clearer, right? Because this is taking all the sum over R dimensions. Okay. And later we will take K dimensions. The first K, we will see it's really equal to sigma 1 square plus sigma 2 square plus all the way to sigma K square. The first K singular value square. Okay. We will show something like that. So this is actually what we call the rank K approximation, right? Because just like you do PCA, right? So your purpose is not to recover all the R dimensions in the data because maybe the major components are important. And the other components are simply noise. Right? So it's the very, very minor component, which is caused by measurement error. Right? We want to drop them. Right? We want to take the top K most important components. Okay? So here is a redefinition. If you look at what we previously have, we say, hey, this A matrix all the way to R dimensions. Okay? Now we are saying that, hey, it just takes the first K, right? K can be just the 2 for them. Right? Of course, it cannot go beyond R. It can be just the first K component, right? And oh, by the way, we'll take attendance at 7, okay? And so what we want to show is this, right? So keep in mind, Frobenius norm itself is a matrix size, right? It's matrix size, but you can define a distance out of it, okay? You think about it. What if you have a 0 matrix, right? Every element is 0. That Frobenius norm is also 0. Right? Every element square sum. Right? Every element 0, then it's basically 0. Right? And you can, if you want to say, hey, how far away are these two matrices, A and A, right? Your first K component, right? It's really you take the minus, right? And the rest you take the square. Okay? If that is equal, it will be equal to 0. Okay? It's really distant. The more different they are, the larger this value will be. Okay. So this is actually often used in machine learning. So you do the derivative to this A, and it will be equal to trace kind of transpose. Okay. But again, so these are not required for this course. Okay, so you can safely ignore it if you don't know. And here we want to show that the distance between A and AK is going to be closer for the distance between A and B. Okay, when we measure the matrix distance in terms of Frobenius norm. Okay, so this is what we are trying to show. And because of this reason, we say, hey, this AK is really the best, right? So all the other B's are not so good, right? Well, of course, this is not the case, right? We can put B equal to A. This is going to be 0, right? This is not going to be 0, right? You still have some component from K plus 1 to 1. Right? What we want to show is that under the same condition, right? So among all matrices B, such that its rank has less than K, right? It's really, the information in the matrix B has no more than K dimensions, right? So it's like a manifold in something, right? Low dimension, low rank, okay? A simpler shape, right? Okay, if that's the case, among all such rank K or less, matrices, AK is going to be the best. Okay, the one that closest to A, right? So this is the constraint we have. And the question is here. If not, we will continue. Okay. We want to show that AK is the closest among all the rank K matrices or less than K. This is like the budget you can allow, the complexity you allow for matrices. Right? Basically, you don't allow noise, right? So you allow major components at most K of them. So again, here in order to show this, we will prove a lemma. Lemma is a for doing some preparation to prove this theorem. Right? Okay. So we want to show, assume that right? So we have the rows of AK, right? So it's really those rows of AK are projections of A on these K dimensions. Okay, right? It's not difficult to see. We just look at this AK and this is like the K dimensions, right? And these are like the coordinates on the K dimensions. Okay. So let's give some additional analysis of them, right? So we know that this A row is in R-dimensional space, right? It's in R-dimensional space. But now AK only contains the first K dimension, okay? Right? So how do we represent projection of A on the first K dimension? Right? It's something like this, right? Okay. So this is like the difference of V1, V2, V3, okay? And this is the component. This is a component along this direction, right? This component is the first component along the second, okay? So you may ask why we have a transpose here, right? This is because whenever we talk about a vector, it's always column vector, but a special case is for AI. AI is a row vector, okay? The first row, the second row, the third row, A. And so we also want a V to be row vector, right? Because this is scalar, it's an inner product, okay? So that's just that. And then we think about the projection of the whole matrix A, which is a bunch of rows, AI. Okay? So this can be derived similarly, right? So we know this thing is what? This thing is a column vector of the inner products, right? So, AI, VI, A1 VI, A2 VI, inner product, okay? Something like this, right? So this is a column vector and this is a row vector, right? So, yeah, this is a row vector. It's Vj itself. Okay, so this gives you a matrix, and you are summing k such matrices. And so if you look at how to say this. So this A, when you project here, you can. It's like you stack A along this direction. You are also stacking this along this direction, right? So you can look at these projections, right? It's like a stacking of the projection along the rows. Okay, so that's what this thing means. Okay, and now let's look at what will this be, right? So this will be, if you remember, as we repeatedly tell you, right? A VI is equal to what? Sigma I rho UI. Okay, right? Sigma I. Yeah. Any question?
Thank you.
Right. So yeah. So A VI is equal to sigma UI. This is following the definition of UI. Okay. And then we can write this to this. So, right. And we know this thing is what? This thing is AK. This is how we define it. Right. So basically, we are saying that the projection of the matrix onto these first K dimensions is really just AK, right? So this is kind of like, you know, when you project your whole space project to this subspace, right, is AK. This is kind of your closest projection, right? Now we want to show that for any other B, right, your projection is going to be larger or equal to this, right? No smaller, right? So let's assume that we have a rank B matrices, okay? And you know, this B will already minimize A minus B for B. We want to show that, you know, it's B will be AK, right? So they're minimized, but this AK is even more minimized because we will show that AK is more. Right? So AK is really minimizing this distance. We assume that B, which is different from AK, is minimized. Then we show this is not possible, right? Or unless it's AK, right? So if rank B is smaller than or equal to K, and B minimizes, right? So then we can show that each row Bi is AI's projection onto the V space, okay? Because now we are thinking about a particular different space, V, right? Which rank is also. So they are defined by these K dimensions, right? And then you think about, you know, this is already so this is original A, still A1, A2, AJ, these rows, but we want to map to this space. Okay? So when we can minimize this, right? Okay, this is only when, you know, Bi, this Bi is AI's, you know, projection onto B, right? So D is also have for each row, right? This AI's projection onto this space is B1, right? A2's projection onto this B2, and this only when it's projection. Why is this a case? Because if you have some component of B, right? This row has some component, which is actually, you know, not AI's projection, it's perpendicular to AI, right? Then you can eliminate that, right? So you replace that, it will reduce this value, okay? Because these components will only add to this row's magnitude, right? So put simply, you know, this is Frobenius norm of A, right? So this is row and this is each row square, right? And we can show that, you know, AI's component is, you know, perpendicular to V, right? I mean, the V is a spanning of V, right? They cannot be reduced by V, okay? Right, because, you know, when you reduce something, right? So this is A1, right? And you want to minimize their distance, right? So B1 must be in this subspace, it's okay? Right, so must be in this K-dimensional space, right? And this is row number, by the way. This is the vector. This is like V in this space, right? Okay. Although the notation kind of similar. And when you minus this component, right? If this is in R-dimensional space, right? And this is in K-dimensional, B's K-dimensional space, right? But if you think about it, right? If you have some component totally orthogonal to this space, it cannot be reduced by this component, right? So the only way that you reduce it the most is if your Bi, right? This row is AI's projection onto it, okay? Which means AI's all the components of AI that is in this subspace is removed, right? So this, right? So that's what it means. Let's continue. Yeah, so then, you know, A minus B Frobenius norm equal to sum of square distance of rows of A to V. V is this subspace, okay? Right? Because, you know, all the components, right? So if you remember, we have a plot, right? And this is the subspace, right? V, okay? V1, V2, right? And all the components along the subspace, you know, A mapped to the subspace is eliminated. The rest are those subspace. Sum of square distance of those A to V, okay? Right. So, you know, AK minimizes the sum of square distance of rows A to any K subspace. Right? So then we have this. Right? Because, you know, this is a sum of square distance from rows of A to V, right? It could be a particular space, right? And the AK minimizes such any such space. This is by our proof. Right, so our proof here, right, the projection of A, right, and is AK, okay? Projection of A to the span of V1, V2, right? This is because this is the best fitting case, K-dimensional space, if you remember, right? So we proved the optimality of best fitting, right? So AK is the best fitting space, and B may not be the best fitting, right? If B could be the best fitting, then it's no better than A, okay? So because the best fitting K-dimensional space is we choose V1, V2, V3, but in that way that maximize the components. Okay, so because AK is the best fitting subspace that we showed earlier, then AK minimizes sum of square distance of A to any space, right? Because that space, but A1 to V1 to Vk is the best fitting. Okay, so this V can be no better. Okay, so that's why we have this relationship. So put simply, AK is really the closest to A, right? The best you can find among all possible B's, right? So this is kind of like we are repeating what we proved before, but just to memorize this conclusion good enough. Okay, so among all rank K or less matrices, right, approximate A, AK is the closest. AK is really the best, right? So next, we will show this, right? This is Frobenius norm. What if we change to another norm, right? So like 2 norm, okay, L2 norm. No, 2 norm, okay. For matrices, 2 norm, for vectors, L2, okay. We can show that they are the same, right? So let's look at this. So firstly, we want to define what is P norm, right? So because we want to also show 2 norm, right? So we need to understand what is 2 norm, which is a special case to P norm. Right? The P norm is something defined like this. Okay, let's say you have a matrix A, and previously we have Frobenius norm. Right? There's also a concept called P norm. P is for example, integer number. Okay, and you can have, what is P norm? P norm pretty similar to our previous case, right? Previously we have 2, right? But now it's P, LP norm, right? So by the way, this is a P norm of a matrix. Okay, this is the LP norm of a vector because when your matrix times the column vector, it's a vector. Okay, so the P norm is defined based on the vectors LP norm. Right? And here we are saying that, hey, we want to rotate all possible directions using a unit vector and find the particular x that could maximize this linear transformation after rotate, right? Transform to another vector. We want to maximize its magnitude, right? If it's 2. Right? Here it's P, LP norm. Okay. So what is LP norm? I hope you understand, right? So LP norm, for example, you have a vector which is x1 all the way to xd, d-dimensional vector. Okay. So LP norm is taking, square root p, right? x1 p plus x2 p plus dp, right? To the power p, right? So you can also write it like this. Maybe it will be clearer. Okay. So this is for a vector. This is a vector. Okay. This is to the power of 1 by p. So this is called the LP norm. And in a particular special case, we have the L2 norm. Right? So this is square, and take square root. So this thing is called a square. This is really the vector length. Right? So in 2-dimensional, 3-dimensional, you can see it's vector length. Okay. But if you look at in the Euclidean space, so if you look at more than these dimensions, it's still, LP norm. Okay. Yeah. So that's basically the norm here, right? And so actually, if you remember how we define sigma 1, it's really 2 norm of A. Okay, 2 norm of A. 2 norm is also called a spectral norm, by the way. Okay, this is just a terminology. Right? Why? Because you think about what is 2 norm, right? This is really, this, right? So we are saying, hey, we have a unit vector and rotate any direction, right? And we want to maximize this. This is equivalent to max. Right? It's upper bound or something, largest possible value. Okay, supreme, right? So, and here you can see that, hey, we are not talking about a unit vector, right? But here, we normalize this, right? We have this factor, but we normalize it. It's like we require X to be a unit vector. Okay, they are equivalent, right? So really, sigma 1 is really L2 norm of A. Okay, the first singular value is L2 norm of our matrix. And in general, we have this relationship. Okay, L2 norm is gonna be 2 norm is gonna be smaller than or equal to Frobenius norm. But the reason very simple, right? If you look at 2 norm, what is 2 norm? 2 norm is, is a L2 norm, right? Vector L2 norm. This is the vectors size, right? But the Frobenius norm is all the rows, all the columns, right? It's all elements squared, right? So this is going to be much larger than this, right? But again, this Frobenius norm cannot be infinitely large. Okay, it's bounded by this. Okay, by this thing, this 2 norm times square root of. Okay, we can prove this, but you can just remember their relationship here. Okay, now let's take a look at what we can do with, SVD, right? So, I mean SVD, but with rank K approximation, right? So we just take the first K component, right? What can we achieve? First, let's look at a database. Okay, here it's, by the way, it's a toy example, right? So we have a database of document and term, right? So you have an article, right? But you have a dictionary of terms. Right? Maybe you label them as the zeros term, first term, second term, each is a unique word. Okay, and then you have a document, and for the document, if a term appears, you label this as 1. If it doesn't appear, you label as 0. Then you will get a row representing that document. Right? So the D is how many words you have. This is how many documents you have. And of course, you can go beyond that. Right? So how many times this term appears, right? You can also encode that in this document. Okay? Maybe this is the word zip, right? THE, and appear in the document for 800 times. Then it's here. Right? So you can have a matrix like this. Okay, we can then pre-process, this matrix A to answer similarity requirements. Okay, basically we'll not take all the components, we just take the K components, not all the R components. Right, let's take a look how to do that. So firstly, let's define what we mean by similarity curve. Right, so let's assume that we have n documents already, right, in the database. Okay, and we are representing them as a term list, right? Term adjacency matrix. Okay. All right. So how can we answer the similarity queries? And we are given a new document, right? We want to compute how similar this document is to each original document, right? So we have n document 1, 2, or 2. Right? How close this document is close to this document? How is it this document? How is it to this document? So this is what we call the similarity curves. Right? How can we represent this thing in matrix form? Right? We can. The output is something like this. Okay. Right. This is called a vector of similarities. Why? Think about it. Let's say this is A. Right? So this is your first article A1. Okay. Second article A2 in the database, and this is your nth article AN. Right. And now you have a new article comes, which is in the column. Right? This is X1, right? So actually, you don't care about it. It's a column vector, right? So the original article is represent a row vector, okay, X. And we said that you can represent something by block matrix notation. You can represent this thing as this times X, all the way to this times X, right? And what is this? This is inner product from the first article and the new article. Right? This is inner product, second article and the new article. Right? And inner product does reflect the similarity because you think about what are they? They are d-dimensional, right? So both are d-dimensional. They are the word co-occurrence, right? If these two words co-occur, then you have the counts and you time them, right? and sum with the other word. Okay? If they don't co-occur, that's something 0. Then you have sum of 0. Okay? So this is the inner product, reflect the similarity. So the output is really a vector, where the first element is similarity to the first document with X. The second is the similarity with the second vector, A2, with respect to X. Okay? So this is the problem we are looking at. Right? And a naive approach to do this kind of computation will take ND times. Okay? So this is very simple to see. Right? So you have a matrix, which is n by d. Right? So A is n by d. Okay? And you have a column vector, which is d dimension. Right? So you think about it. This is d by d. Right? So this is the cost of d. Right? And the second row is another d in the product. Okay? You have n such d's. Right? So you have n by d. Okay? That's the cost. All right. So now what we do is we want to do a kind of rank K approximation. Right? Instead of go all the way to R, right? And we just use the first K dimensions. Okay. So basically, we take V1, V2 all the way to Vk. So how much can we save here? Right? We are still doing this, but we are approximating. So now instead of saying, hey, I do AX, I will just do AKX. Right? This approximates A. This, remember, this is very close to A. Right? It's compared with other B's. AK is probably the best if you just consider K dimensions. Right? So now let's just put this thing here, right, times X. So this is AK. Right? And let's see what it will give us. Right? So here you need some trick to see the cost is reduced. Right? So first thing is you need to realize, hey, this thing is an inner product. This gives you a scalar. This is a value, okay? This is scalar. Sorry for the handwriting. So this is scalar. Okay? Right. This is one particular value, right? So this thing is a scalar. This thing is also a scalar. So only vector is what? The only vector is this one, right? The UI. Okay, these are these values. Right? So so this is one thing that you need to pay attention. Secondly, think about, right? So we need to do this thing K times. Okay, within each item, first you compute a inner product of this to get a value. Right? So what is inner product of this? So we know that K is d-dimensional, right? VI is also d-dimensional. So this is really d, right? And we do this K times. Okay, it's KD. After that, this is one value, this is one value. This is what? This is a, UI is a n-dimensional vector. And so remember U, right, and D and B. Okay, so these are how many rows you have in the A, this n-dimension. Okay? So and the n-dimensional vector times some constant. Its constant is n, and you have k of them. So this is nk, right? So you can see the cost now becomes, k times n plus d, right? And k is some small number, right? The first k, maybe 10 or something. And what's the previous cost? Previous cost n times d. So that matters a lot. You think about d is the number of possible words, right? It could be 10,000, right? N is even more. Maybe you have 1 million documents, right? Then they're timing them together is going to be crazy, right? N plus d is going to be much smaller, okay? So this actually saves a lot of computation if you just compute this. Another thing that is nice is that there's an error bound, right? So you remember that we have a conclusion. Let me see where the conclusion. We have a conclusion that so this is how far away you are. So this is your desired similarity vector, okay, vector of similarity. This is your approximated result. Okay, if you compute that difference, it's this thing, right? But this thing is quite tricky because you can have different query documents, right? X vector, it's a water vector, right? And for different X, you will get different result, right? So the similarity vector will be different, approximately, right? The difference vector. But we know that, we told you that there's 2 norm, right? 2 norm, matrix 2 norm is the upper bound, right? It's the max of this, okay? So because we define 2 norm in this way, right? Okay? So this is what we define as 2 norm. So this is really the upper bound. So here, no matter how x you change, okay? So this is gonna be, this value is gonna be upper bounded by, the 2 norm of A minus AK, right? Any question here? I hope you can follow this. All right, so now let's do some analysis of what this is, right? So you think about it, right? So A is what? I equal to 1 to all the way to R, right? Minus AK, AK is 1 to K, right? So the rest is K plus 1, K plus 2, all the way to K plus R, all the way to R, right? Okay, that's the component. And we know that, as we define, okay, 2 norm of a matrix is the matrix sigma 1, okay? Right, the first singular value. Right. But what's more interesting is that, this thing is actually equal to this thing, okay? So if you remove the first K component, then now the next most important dimension is K plus 1's dimension, okay? But this thing, we use the red to denote it, right? Because we will prove that later. We cannot prove it right now. Okay, we will have to first prove that the UIs, right? We define UI as, AV divided by sigma is U, right? So we first need to prove that UIs are orthogonal, and then we can see this, right? So that's what we are gonna do next, which is to prove the left singular vectors are orthogonal. Okay, this is not all, these are this type. And before doing that, let's take attendance, right? I think it's different goal. Okay, what I will do is I will sample some. Okay. Sai, here. Sai Sanjay Akula.
Yeah, I'm here. I'm here.
Thank you. No, we skip 5. Okay, 1, 2, 3, 4, 5. Okay. Ankat, are you here, Ankat?
Yeah, I'm here.
Okay. We will skip 5. 1, 2, 3, 4. Okay. Jie Chen, are you here? Oh, I think Jie probably asked for leave, so we will leave. Okay. 1, 2, 3, 4, 5. Achut, are you here?
Yes, Professor, I'm here.
Okay. 1, 2, 3, 4, 5. Varun, are you here? Varun.
Yes, I'm here.
Okay. 1, 2, 3, 4. Okay. Paid Ali, are you here?
Yes, I'm here.
Okay. 1, 2, 3, 4. Okay. Archana, are you here?
Yeah, Professor.
Okay. 1, 2, 3, 4. Okay. Devanshi, are you here?
I'm here.
Okay. 1, 2, 3, 4. Taylor, are you here?
Well, hello, I am.
Okay. 1, 2, 3, 4, 5. Bilawal, are you here?
Yes, sir, I'm here.
Okay. 1, 2, 3, 4. Okay. Zheng Zhitan, are you here? Zheng Zhitan.
I'm here. I'm here.
Okay. 1, 2, 3, 4. Priya, are you here? Or Priya?
She's here. She's here.
So it's a little confusing, right? So You mean you in the same computer? Masha? Hello?
She's my roommate. She's here. She's right here.
Okay, got it. Okay, just want to make sure. 1, 2, 3, 4. Cranty, are you here?
Yeah, I'm here.
Okay, thank you. Let's go to the next list. Muhammad Kamal, are you here? Yeah, I cannot hear you, but I see your name. Okay, so I think I will take you. Okay, so yeah, it's fine. Yeah, I see your name pop up. Let's go back and continue. So here, let's see. So previously we defined what is UK, right? So UK, if you remember, right? So we say, hey, UI is equal to what? It's equal to A times VI, right? But we need to divide by sigma. And you know, sigma is actual normalization, right? Because sigma itself is AVI's O2 norm. Okay, it's fine. Right? So UI is definitely a univector, but one piece is missing, which is, you know, we know VI are orthogonal, but how do you know that after transformation with A, these UIs are still orthogonal? Right? This thing is a missing piece, right, in our definition. Right? We want to complete the puzzle. Okay. So our proof sketches something like this, right? We want to show, hey, U1 is orthogonal to U2, U3, U4, right? And then we know that U1 is orthogonal to everyone, right? And then let's get rid of U1. We show U2 is orthogonal to everyone, okay? And then we show U3 is orthogonal to everyone after, okay? Blah, blah, blah. Okay? So, but they are quite similar, right? So they are symmetric in some sense, okay? So we only need to show that U1 is orthogonal to U2, U3, all the way to UK. Okay? Then the others are similarly proved. Okay? So how can we show this, right? So we want to show that any I from 2, okay, is orthogonal to U1. So the solution that let's assume that this is not the case first, right? Then we show there's a contradiction, right? Proof by contradiction. Okay. So so you know, if you know UI and U1 are not orthogonal, so their inner product is not going to be 0, right? It's going to be some value. Let's say we call it delta, right? And we assume the delta is larger than 0. But this is not a problem because if your delta is smaller than 0, right? So then you reverse the direction of UI. Then you get a delta. If your previous value is smaller, negative, reverse, it becomes a positive. Okay? It's a reverse, you know, it's absolute value of that. Okay. So now with this assumption, let's think about whether this will lead to conflict, and then showing that delta have to be 0, right? And this is by constructing a new unit vector, okay? A new vector v1 prime from v1, okay? But v1 prime, we want it to be a unit vector, okay? So we create this thing, but we divide by the length of that vector. So we normalize it, okay? So how do we create it, right? So the thing that are in our question is u1 and a ui, right? So they are coming from v, if you remember. This is coming from vi, this comes from v1, right? So of course we need to go back to v, because they are orthogonal. We want to utilize some their property. Okay. So let's construct this v1 prime. It's equal to v1 plus vi. Okay. But v1 is, let's say, this one. Okay. And vi is orthogonal, right? So it's something like vi. But what we will do is we will not go all the way to vi. We will get a small epsilon along that direction, and then we compute this factor, right? This factor equal to their summation. I hope this is fine with you guys. Right. But this is going to be larger than 1, right? Because this factor is 1. Okay, this is going to be large. So you need to divide by this, right? So v1 prime is still a unit vector. And it's not difficult to see, right? So because, you know, these two vectors are orthogonal, right? v1 and the vi. This is by our selection of v, right? Every vi is orthogonal to the previous piece. Okay. And because of this reason, you know, if you look at this length is 1, this is a v1, the unit vector, this length is epsilon, right? So what's this length? It's this one, right? It's 1 squared plus epsilon squared x squared, right? So now we have this view, and V1 is really a unit vector. Okay, so this is we rewrite it here, and now we also assume that these two are not orthogonal. We have some more delta component here, and now what we can do is, so what if we do the A times this unit vector V1 prime? Right? What will be the result? Okay, let's take a look. So A times this one is gonna be you times A here and you times A here, right? And A times V1 is sigma 1. Okay, A times Vi is sigma I1, right? So this is how we get this thing. And next, let's look at what we can get, right? So again, here's we need to use a lot of inequalities. Okay, so we will describe them shortly, so that you don't feel confused. Okay, there are some tricks, right? So for theory people, they need to memorize maybe 20 or 30 inequalities, right? So we will tell you some of the inequalities that we are using. Okay. So let's look at this. This is a vector, right? So this is another vector, okay? Because it's a matrix times a column, okay? And it's a unit vector. Right? It has length at least as large as the component along U, okay? Because this is a vector like this, right? It's now convert from V space to U space. Right? Now let's look at what if its component along U1, this direction. What will be the size, right? So we do a inner product, right? So because this is one unit vector, we just do inner product, and this with this vector. Okay. And let's see what were the calculations here, right? So firstly, one thing you can see is these two, because this is a unit vector, it's less than 1, so you get this. Okay, these two time together. The second is if you look at this and this, right? This and this is delta, okay? This is what we assume. Okay? So that's why it's slow, smart. Right? So this is equal, right? So what is larger than is really from this component, okay? So what is this component, by the way? This is 1 plus epsilon square, take 1/2 square root, but negative, because it's at the bottom, okay? It's a numerator. Okay, so keep in mind of this, right? And in order to show you this, let's go through some conclusion here, right? So we have so-called a Bernoulli Equality. It states something like this. Let's say n is a integer which is larger than 1, maybe 2, 3, 4, right? And if x is larger than -1, which means it's 1 plus x is positive. Okay, we always will have this relationship. Okay? 1 plus x to the power n is larger than 1 plus nx. Okay? So this has been proved. This is some inequality people need to memorize. Okay? And here we need the n to be an integer larger than 1, right? So in general, you can have this zero. Okay. So this a now can be not an integer, right? But if your a value is larger than 1 or less than 0, you have this relationship. Okay, but it's kind of preserved because this is basically n is a, right? Larger than 1. But if your a value is between 0 and 1, okay, if it's between 0 and 1, then you have the reverse direction. Okay? Which means for the majority of the time, this thing is going to be larger than this. Okay? Now let's go back to this term here that we derived here. Okay? This term. Right, so let's take a look at this equation. Right, so this is 1, okay? X is sigma squared. That looks pretty nice, right? A is negative, right? It's a negative value, okay? So that's really its logic. Okay? So if you search for the inequality in Wikipedia, you will find it. Okay, so it's a very famous one, but yeah, so people has to memorize maybe 10 to 20 such things. Okay? We'll see another one that you need to memorize later. Memorizing them will facilitate your derivation a lot. Okay? Otherwise, it will be super complicated. So here you can see, hey, this is a relative thing. Right? So because this divided by this thing is equal to times something like 1 plus epsilon square. Okay, is minus 1 by 2, because the minus is divided, but now it's times. And this is equivalent to is 1 plus takes this down here. Okay, so takes this down to minus 1 by 2 times this x. Okay, so that's how we get this. And this is by generalized Bernoulli inequality. And then we time them out, right? So how we time them out? So this term with this term is gamma 1, right? And this term with this term is minus 2, right? And then we come to this term with this term, right? And this term with this term with this term with this term. Okay, so this is basically how we get the expanded to here. Now let's take a look at what we have. So think about epsilon. Epsilon, when we construct it, we never say how large it should be. It could be 0.1, it could be 0.01, it could be 0.00001, right? So you can have a very tiny number, okay? So that means no matter how large these components are, right? We can make them very, very small, much smaller than this one, okay? Right? Because you know, if you are 0.01, okay? Then square is 0.0001. And the cubic is even, this is 10 to the power of -2. This will be -4. This will be -6. Right? And these values will be negligible, right, compared with this one. Okay. If you think that's still not enough, then you can further decrease epsilon. Okay. But finally, you can make these two components really negligible compared with this term. Okay. So that means you will have a positive term standing out. So this thing is larger than epsilon. It's okay? I hope this is fine. And what does this mean? Right? For sufficiently small epsilon, you will have this conclusion. But keep in mind, epsilon 1 is if you have an A and you have an X, which is a unit vector, right? And by the way, V1 is also a unit vector, or we normalize it. Okay? Then we rotate all X possible values. This is the largest possible value for this. Okay? So you cannot find an even larger value, right? Let alone this new vector has a component along U1, okay? This component is even larger than this. This is a contradiction, okay? Right? Because sigma 1 is really the largest, right? You put V1 here, you can see V1 is maximized this. Right? Now you find another one which is even larger. Okay? Because this one, why it's even larger, right? So it's because its small component is already larger, okay, along U1. Right? So this is important. So because of this reason, we have to, this will not hold, right? We have to make them zero, which means U1 is orthogonal to M1. Okay, so that's by construction, we can show that, you know, the left singular vectors are also orthogonal. Every two of them also. Any questions here? I hope this is fine. Okay. Yes, this is called Generalizer Bernoulli Equality. So keep this in mind. Okay. Okay, so yeah, so let's look at the theorem that we talked about. Right. So previously we said, hey, if you minus the first k component, the rest of the component, the largest information is the k plus 1's dimension, the k plus 1's magnitude. Okay. So how can we show this? And remember, right, so we A is from I equal to 1 to R, right? AK is I equal to 1 to K, right? So the rest is really from K plus 1 to R, okay? So that's what we have remaining. Okay. So let's assume this thing, basically it's this, right? Let's assume V is a top singular vector, right? We will show that V is really K plus 1, okay? So let's write V as something like this, right? Because V is still in this space, R-dimensional space. We can write things like this, the coordinate along each dimension. And now let's look at the, you know, if we have this matrix times this V, what we have, okay? So here we are putting this thing to here, because this thing, times V, and V is this thing, okay? Putting this back. Right. And then let's look at what we look at, right? So, how to see this, right? So now you should be super familiar with that, right? If you look at this term here, right? So you know, each term is something constant. Right? This is the constant can move forward. Then we have Vi in the product Vj. And for ij that are not equal, they are orthogonal. This term will be 0. Only one term that can be that, which is, when this j is equal to r, which means it's Ci times Vi. And when this is Vi, they cancel, right? Because the inner product is 1. Okay? So this is really Vi, Ci, sigma I. Ci moves to. Okay? But because these two terms are 1. Okay? So you can further eliminate these two terms. Right? And then you will get this thing, and we are using our conclusion. Right? So that's why we need to prove this later. You know that U1, U2, U3, they are all something. Okay? It's like this is U1, this is U2, this is U3. Right? And now these are the coordinates now. Right? So then if you compute the L2 norm of that, that's basically x1 squared plus x2 squared plus x3 squared, something like this. Okay. Right. And now this looks fine so far, right? So, but which V will make this largest, right? Because we want to maximize it. Okay. Right. Because it's a 2 norm, we want to maximize this one we time V. So you think about it, there's a constraint on V, right? Because V is a unit vector, which means all these Ci squares, right, plus equal to 1. Okay? So this is the constraint here, right? But you think about these components. Right? So you think about C1 all the way to Ck, right? Then we have Ck plus 1 and the plus 2 all the way to Ci. Okay? But it makes no point to allocate. There's a budget one. It makes no point to allocate anything to here, because this summation starts from k plus 1. Okay? You are wasting the budget. It will not increase it. Okay. Now let's consider how we allocate those budgets. Basically, it's saying, hey, k plus 1 to r, right? How we allocate them to here. Right? And it's apparent that if you look at to concentrate on all components here is the best. Okay, because the sigma is decreasing, right? The largest is sigma k plus 1. Sigma k plus 2 is going to be smaller, and k plus 3 is not. So even if it's not square, right, it's like a summation is 0. Okay, you should already concentrate on 1. Okay, now it's even square. Square will make smaller things even smaller, larger things even larger. Okay? So if you have originally 1/4 and 3/4, right? If you square them, it will be 1/16, right? And this will be much smaller. Okay, compared with this. So if you concentrate some here, and after square, this is even more concentrated. You will make this term large. So this you boost this sigma k plus 1 even more. Right? So this is only when these terms are 0, and this is 1, right? And all the others are 0. You are the largest. So what does that mean? That basically means that your V is 1 times Vk plus 1. So your V is really Vk plus 1. When it's Vk plus 1, right? So then this is the top singular value. Okay, and when you have Vk plus 1, the associated singular value is sigma. Okay, so that's basically the conclusion here. But any question about it here? Okay, so again, another thing that if you put this thing here, Vk plus 1, okay. So it's this thing is equal to So AK times this is 0. Right? You need to pay attention. These rows are within the first k dimension. Okay? This is a k plus 1 dimension. Yeah, also, it's really still a. Okay? There's no minus this thing is gone. That's why it's still the singular value of the original. Okay. Okay, so I think we will continue next time to show that even beyond the Frobenius norm, even for 2 norm, AK is also the closest. Okay. But we'll stop here, and I will take your questions. If you have no questions, that's basically the end of the class. Thank you, and have a good evening.
Thanks. See you next week.
See you.
Bye.
Yeah, if you have any question, it's the time to ask.
Just double checking. This class has no midterm. Is that correct?
No, we don't have midterm. We have the program projects and 2 written assignment and the final project. Okay.
Okay, just double checking. Other courses are bringing it up.
Yeah, sure. Yeah, I confirm there's no midterm. Any other questions? Yeah, because we want to make it a little bit hands-on, right? So this theory kind of stuff, we only have 2 of the topics. Okay. It may be a little bit headache, by the way. We previously, the course, we have 6 of the topics. We reduce it. All right, so it seems as there are no more questions. So we will stop here, and the video will be uploaded, and we will also have our annotation assignment maybe released either tonight or maybe tomorrow. I will see you guys next week at the same time.
Non è po' senza gazzette da